Okay, I think it's time to start. So we resume our conference, and it's my pleasure to announce the first talk. So the speaker is Professor Malikov, and he'll talk on averaging of random groups. Please.
Okay, thank you. Hello, dear colleagues. Can you hear me?
Yeah, it's okay. Yeah.
Okay, thank you. My name is Artur Malikov, and I am student at MIPT, Moscow Institute of Physics and Technology. And today I'm going to talk to you about averaging of random groups associated with nonlinear differential equations. This study was done jointly with Sel Janovich Sagbayev. And there will be two main ideas, parts of my talk. Firstly is regularization of differential equations, so whose solutions aren't defined for all t, and the next part is namely averaging of random groups. So firstly, there will be some introduction, some base idea. After that, the development of this idea is regularization for arbitrary power. And after that, the main part of my talk or this study is namely averaging of groups associated with nonlinear and linear partial differential equations and law of large numbers. And lastly, there will be some future plans for Fujita's equation. So let's start and let's consider an equation. First derivative of x is equal to f of x is equal to x squared. And function f has not bounded derivative. And from the theory of differential equations, we know that the solutions aren't defined for all t. But we can make the change of variables x is equal to tangent of theta, and new equation in terms of theta is first derivative of theta is equal to f1 of theta is equal to sine squared of theta. And new function f1 has bounded derivative, and solution is defined for all t. This change of variables has geometric sense. This is almost stereographic projection, and we consider our equation on the circle after the change of variables. On the slide, you can see graphs of the solution. First graph is, if to be accurate, is two solutions of the initial equation, and the second figure is solution of the differential equation after the change of variables. This was some base idea, and the development of this idea, these conclusions, is arbitrary power. So let's consider an equation first derivative of x is equal to modulus x in the power of beta, where beta more greater than 1. You can see it on the first line on this slide. Function f doesn't have bounded derivative, and solutions is not defined for all t, but we can make also change of variables. You can see it on the third line of the slide. Is a bit more complex, but we obtained the differential equation in terms of theta. First derivative of theta is equal to beta minus 1 times sine squared of theta. And also solution is defined for all t. From the theory of differential equations, it is known that the solution of these equations don't cross 0, don't intersect and don't cross 0. But we can consider an equation first derivative of x is equal to x squared plus epsilon. You can see it on the first line on the slide. And by making familiar change of variables, we obtained an equation theta, first derivative of theta is equal to sine squared theta plus epsilon times cosine squared theta. And coming back to the idea of circle, we can study a period of rotation when solutions going on this circle. And in this case, x squared, the period can be calculated precisely. Period is equal to p divided by square root of epsilon. But in the case of x, first derivative of x is equal to modulus x in the power of beta plus epsilon. After the change of variables, we obtain an equation you can see on the second line on the slide. And there is some complexity or some problem that function that stay in the right side of differential equation of theta doesn't have bounded derivative in the neighborhood of 0. But we can, in the neighborhood of 0, consider initial equation, and in the neighborhood of infinity, consider the second equation after the change of variables. And in this case, period could not be calculated exactly, but we can make some intuitively estimation. And the result you can see on the last line on the slide. So the next step of this consideration, these conclusions, is family of solution. We can consider partial differential equation. First partial derivative of u in the order of t is equal to modulus u in the power of beta. And this case is similar to previous, because for each x we obtained ordinary differential equation, and x don't interact in quotations, and there are the same solutions, the same change of function, and the same result for period. So also after that we can consider an equation you can see on the first slide. It differs from the previous case as a times first derivative of u in order to x. And the solution in this case is similar to previous, but there are a shift of an argument, x plus a times t. And now let's move on to the namely randomization main part maybe of my talk. Let's consider an equation you can see on the first slide. First order of u in order to t is equal to gamma times first derivative of u in order to x plus u squared, and u if t is equal to 0 is equal to u0 of x is in Hilbert space L2 of R. After the change of variables, we obtained the equation you can see on the first line. And notice that if u0 is from L2 of R, theta 0 is also from L2 of R. And the second equation generates a group G gamma T. It's nonlinear group of transformation. And the solution theta is equal to G gamma T on theta 0. And we can consider G gamma T as two groups, T and S gamma T, where theta you can see on the next line. Tt is some nonlinear group of certain nonlinear group of transformations, and S gamma T is a group of shift of the argument. And it is important that these groups are commutative. TT S gamma T is equal to S gamma T TT. And for our future consideration, conclusions will be useful next definition. Definition 1, the operator valued function fg with f if t is equal to 0 and g if t is equal to 0 is equal to identity operator are said to be Chernoff equivalent if for every t and every u from x we have, and you can see limit on the last line on the slide. So it's a Chernoff equivalence. And now let's consider some, we have obtained law of such number and described expected value. So in previous case, in our equations, gamma was an random variable, and the group gamma t is also a random group, and S gamma t is also a random group. And it can be shown that expected value of S gamma t, unitary group of shift of an argument, and the S expected value gamma t are Chernoff equivalent. And hence, expected value of G gamma t and G of expected value gamma t also are Chernoff equivalent. And in the second line on the slide, you can see the law of large numbers. It occurs in this case for S gamma t. And it was shown in some previous articles. And for each x from L2 of R, TT x is continuous map from R plus to L2 R. And using this fact and the law of large number for S gamma t, we have obtained the law of large number for nonlinear groups G gamma t. You can see it on the last but one line on the slide. So let's move to the same considerations, but in the linear case. So coming back to our equations, you can see it on the first line is after the change of variables. From the theory of differential equation, it is known that solutions of this equation in the first line are dependent from the first integrals of the system of differential equation you can see on the second line on the slide. But we can also analyze a differential equation in the third line. It's differential equation on the function v, and t, x, and theta is an arguments. This is linear equation of v. And this equation, and the solution of this equation is also depends from the first integrals of the equations in the second line. And the third equation on v is generates a linear semigroup, generates semigroup u gamma t. And was obtained the generator of this group A gamma. Gamma is a random variable. A gamma is equal to, by definition, you can see limit, where v0 is from Sobolev space. And on the last line on the slide, you can see the view of this generator. And notice that the result that has been obtained in nonlinear case is more obvious in linear case, because you can see that generator of the group u gamma t, A gamma, has two independent parts, linear with x and nonlinear with theta. And random variables stays in the first part, in linear part. And in the nonlinear case, nonlinear partial differential equation, it appears as commutativity of S gamma t and tt. So next step is law of large number and describing expected values. Expected value of u gamma t and u expected value gamma t also actually equivalent. It has been shown, and also law of large number occurs for semigroup U gamma t. You can see the law of large number in the second slide. And so, in addition, we can consider another pair of differential equations, very similar to previous equations. So let's see on the third line, you can see equation. The difference from the previous case is gamma divided, random variable gamma divided by 2 times square root of t. This equation generates not group, but a family of linear transformation, t with tilde, gamma t. And next equation is with second derivative of v in order to x, partial derivative in order to x, and this equation generates linear group of transformation, semigroup transformation, t with hat t. And we have shown, that expected values of t with tilde and t with hat are Chernoff equivalent. And notice, and it worth emphasizing, that all these considerations and conclusions could not be made for the initial equations. So for the equations with U squared, because this equation can generate a group defined for all t. So the regularization was very useful for our conclusions. And so some future plans, Fujita equation, you can see it on the first line. And first derivative of U in order to t is equal to second derivative, partial derivative of U in order to x plus U squared. And after the change of variables, we obtained the equation that you can see on the second line, of the slide. And there are two main approaches. And there are two main approaches to analyze these equations, is namely after the change of variables, trying to get regularization, or using averaging some random differential equations. So I have some time, and let's see some key point of this work. And firstly, we obtain regularization for arbitrary power for autonomous differential equation. After that period of time, as next step in this idea, as rotation of the circle was obtained. And next step was family of solutions, but the main part is random equations. And maybe the main part is the law of large number for nonlinear groups associated with nonlinear partial differential equation. After that was some linear view on this problem. And maybe that's all I want you to say. I was too fast.
Okay, thank you. Are there any questions or comments? Well, if so, probably I have a somewhat even naive question. Your first law of large numbers is just a corollary of a known result, right? So
no,
it's smallest easy, right? Or just yeah. Well, just this main implication on this page. Once we know the result from this one theorem phi.
Just one moment.
I mean, it's difficult, or just we just apply, do something.
It is important in the case of nonlinear groups that S gamma T and TT are commutative groups, and also that TT of X is continuous map. So it's not just corollary from the second line, but there are also some some
auxiliary conditions, right?
Yes, yes.
Okay, okay.
Thank you.
Okay. So any other questions? Okay, if not, then we thank the speaker again. Thank you.
Thank you very much.